Dear students, we are again on haloalkanes and haloarenes. We have solved a lot of questions which involved preparation and properties of haloalkanes and haloarenes. In this video, we will discuss a compilation of all the reactions, many reactions that you have come across in this chapter. Alright? So here we have the first question. Discuss the mechanism. So these kind of questions will help you to get a better understanding and comprehension of the concepts that you have learnt, which will help you to answer multiple choice questions in a much easier manner. Alright? So this is the start. There are two compounds and these are the products formed. So we have to deduce a mechanism or describe a pathway by which you get this product and this product. Looking at the first product, it is quite evident that after the bromine is lost as bromide ion, this lone pair on nitrogen is used to form a bond on this nitrogen, on this carbon, electron deficient carbon. That explains the formation of this product. What about the formation of this product where the 5-membered ring of the nitrogen containing compound is intact without the hydrogen, but the cyclopropane ring has opened up to give you a straight chain, side chain on this attachment on this nitrogen. Okay, so let's see how that happens. So the very first reaction would be, let's understand how the first product is formed, which is very easy. First, this bond breaks. Polar bond, CBr bond breaks and this carbon atom acquires a positive charge. Immediately, the lone pair of electrons on nitrogen will be attracted to this electron deficient site to give you this positively charged species. So now the positive charge is on electronegative nitrogen atom, which has to be neutralized. And how does it get neutralized? By the loss of this hydrogen as a proton. So this hydrogen will be lost as H+, which will combine with Br- to give you HBr, and this bond will be free and will produce 2 electrons on the nitrogen. So nitrogen gets back the 2 electrons, nitrogen gets back the 2 electrons and the positive charge is neutralized. Okay, so that explains the formation of this product. Now, what happens in the formation of this next product? Let's look at that discussion. First step is, before I do that, let me number these carbon atoms 1, 2, 3 and 4. Okay, first step, this bond goes as Br-. Simultaneously, this bond will shift here. Okay, so now you have a double bond between 3 and 4. On the fourth carbon atom, you have a CH3. This is your fourth carbon atom. Now you have a double bond between 3 and 4, correct? Double bond between 3 and 4. Because of the shift of this bond in this direction, 2 will become electron deficient. Before that, 3 is bonded to 1. So this is your carbon atom number 1. Okay? Now, because of all this shift, 2 has become electron deficient, as a result of which the lone pair of electron on nitrogen will be attracted to carbon atom number 2. So this is your carbon atom number 2. So, and when this lone pair is shifted to this position to form a bond between nitrogen and the second carbon atom, nitrogen will lose its hold on this pair of electrons and will acquire a positive charge. And what is the last step? To restore the lone pair of, neutralize the positive charge or to restore the lone pair of electrons on nitrogen, which is accomplished by the loss of this hydrogen as H+. So this bond goes back to nitrogen to restore the lone pair of electron on nitrogen, and H+ and Br- lost here will form HBr. So how did we decide that this bond shifts to form a double bond? By looking at the structure. So by looking at the final product, we can identify what kind of shifts happen and we can describe a pathway or a mechanism. So this particular example was to help you to think on those lines. Alright, let's move on to the next question. Again, write a mechanism for the following reaction. Let's understand the question first. So we have CH2 double bond C CH3, CH2 CHCl CH3 plus methanol. Under normal circumstances, this Cl is lost as Cl minus. So this bond has to break, right? And you get a positive charge on this carbon atom, correct? So ideally speaking, the OCH3, the nucleophile, should attach itself on this carbon atom and you should get a OCH3 on this. On the second position, you should get an OCH3. But that is not the product expected. You have got an OCH3 attachment on the third carbon atom and you have got an OCH3 attachment on this terminal carbon atom. So how do we explain that? Okay. So now, that's what I try to tell you. Looking at the product, we have to think about the pathway. So let's start with the first starting compound. Initially, we do this. Cl is lost as Cl minus, right? And we have a positive charge on this carbon atom. We get the secondary carbocation. Now, since an OCH3 has to be bonded to this carbon atom, we have to convert this carbocation to shift the positive charge from this carbon to this carbon. That is only accomplished by a CH2, a hydride ion shift. A hydride ion from this carbon atom will shift to this position, making it CH2, and now again you have a secondary carbocation. Okay? Now, this secondary carbocation on reaction with methanol, what happens? Oxygen has got two lone pairs of electrons. One lone pair on oxygen will be attracted to this positive carbon. Therefore, this becomes CH3OH plus. The oxygen will acquire a positive charge. And what is the last step? To neutralize the positive charge by losing this hydrogen, and therefore you get OCH3 attached to this carbon atom. This is how you explain the formation of the first product. Going back to this modified carbocation that you got after the hydride ion shift, this can undergo resonance because you have a double bond here on this carbon atom. So when you have a charge and a multiple bond on two adjacent carbon atoms, delocalization can happen. So this pi bond can shift to this position. When this pi bond shifts to this position, you have a double bond between these two carbon atoms, and because a pi bond has shifted to that position, this carbon atom has got one bond less, as a result of which this carbon atom acquires a positive charge. Okay, and this positively charged carbon atom is a stable one because it is bonded to a carbon-carbon double bond. Look at this. Positive carbon is bonded to a carbon-carbon double bond. Okay, so which is an allylic position. This carbocation is stable. This on treatment with methanol. And finally, the next step would be by the loss of a proton, you get the product wherein the OCH3 gets bonded to the CH2, to this positive carbon, which explains the formation of this particular product. Okay, here we have the next question. Which of the following reaction is not feasible? Okay, we have got 4 options. So we have to find out which are the reactions. We look at each option and identify whether the reaction is possible or not. Whichever reaction is not possible is the answer to this question. Let's tackle each of these options, because by tackling each of these options, we get a better understanding of all the reactions that we have learned so far. Okay, let's look at option A. Alright, so I've written down the option A here. Let's see whether these two products can be formed from this starting compound. You notice that the starting compound has a cyclobutane ring. So ring expansion has happened. One is a substituted product, one is an elimination product. Okay, that's very obvious from the products that you see. Alright, so let's see what happens first. First, what happens is this Cl is lost as Cl minus to produce a positive charge on this carbon atom. Okay, ring expansion occurs. This ring, this bond will shift to this carbon atom. It has been discussed in detail. So 4-membered ring gets converted to a 5-membered ring. Maybe let me explain it better. So you have this, let me number these carbon atoms as 1, 2, 3, 4, and this carbon atom is the 5th carbon atom. Okay, so what happens here is, let me redraw this structure like this. Okay, so here we have a C plus and a CH3. This is the carbocation that we get. There is strain in this cyclobutane ring. So in order to relieve that strain, let this bond shift here. So what are the numbers? 1, 2, 3, 4 and 5. Okay? When this bond shifts here, what happens is, you notice that the 3 is now connected to 5. The fifth carbon atom is the one with 2 methyl groups. So let me draw the structure here. Okay? So the 4-membered ring has now been converted to a 5-membered ring. Okay? So let me draw a cyclopentane ring like this. And now let me number the carbon atoms. 1, 2. Okay, so let me start with 1, 2. 2 is bonded to 3. Okay, 2 is bonded to 3. Now 3 is bonded to 5. This is the fifth carbon atom. On the fifth carbon atom, there are 2 methyl groups on the fifth carbon atom, and this is the fourth carbon atom, right? But the fourth carbon atom has lost its hold on this bond. So now the fourth carbon atom has acquired a positive charge. All right. So you have a carbon here, the fourth carbon atom, 2 bonds and a hydrogen, so secondary carbocation. Okay. Methyl shift occurs. This is one methyl group. Methyl shift occurs like this to this position. So now what do you get? Now what you get is a more stable tertiary carbocation. So let me draw the cyclopentane ring. You now have a methyl group here. You have another methyl group here and a positive charge on this carbon atom. This is a more stable tertiary carbocation. The formation of this carbocation will help you to understand the formation of this product. To this positively charged carbon, the OCH3 nucleophile gets attached after the loss of a proton. Okay, so you get OCH3 here. Okay, so this will produce OCH3. Similarly, how will you get a double bond between these two positions? So you have here CH3, CH3 and another bond here. So now a hydrogen will be shifted. So the positive charge is here. To neutralize the positive charge, a hydrogen from here will be lost and this bond will be shifted to this position. That explains the formation of this product. In other words, the reaction under option A is feasible. These two products will be obtained. Okay, so reaction B is not the correct answer. Now moving on to option B, which is very simple. It can be explained just by having a look at this equation. Alright, so you have a Br here. The first step is obviously for this Br to be lost as Br minus. You've got a positive charge on this carbon atom, which explains the attachment of this OC2H5 nucleophile on this positive carbon producing this product. Okay, and then if you have a positive charge on this carbon atom, a hydrogen from this carbon atom will be lost to create a double bond between these two carbon atoms that explains the formation of this product. In other words, option B, reaction is also possible. That is not the answer to this question. Let's look into option C. Now this is option C. When the first step obviously would be the loss of this bromine as a bromide ion, producing a positive charge here. When a positive charge is produced here, OC2H5 nucleophile will be attached here after the loss of this proton to give you the substituted product. Okay? But now, how will you explain the formation of this product? Now, this product can be easily explained. There was a positive charge here, which is what resulted in the attachment of this nucleophile. Now, this positive charge can be neutralized by the loss of a hydrogen atom from this position. If a hydrogen atom from this position is lost, you have a double, the bond shifts here and you will get a double bond here. So these two products can be explained by the formation of a positive charge at this position when the Br is lost as a Br minus. How do we explain the formation of this product? That can be explained in this manner. So I have written down the reactions here. Let me first draw the structure of the carbocation that we first get. So we have CH3, okay, CH3, there is a hydrogen here and now we have a plus charge here when the Br is lost as a Br minus. So to neutralize this positively charged carbon, the methoxide ion can be attached here, or you can have a double bond by the loss of this hydrogen. Okay, so these two products can be explained from this particular carbocation. Now, to understand this, it is very evident that there is a positive charge on this carbon atom. So, some kind of a shift has occurred. What is that shift? So, here this is also a secondary carbocation. What kind of a shift can happen? Methyl group is intact. So, a hydride ion shift occurs. Due to the hydride ion shift, H minus shift occurs. Due to the hydride ion shift, we get a more stable carbocation. So, you have a CH3 here. Okay, you have a CH3 here. Alright. Now, this hydrogen with its bond has shifted to this position to neutralize this positive charge. This becomes CH2. Simultaneously, a new positive charge is created here. You get a more stable tertiary carbocation here. This on treatment with ethanol will result in the final step where the ethoxide ion gets bonded at this position as a nucleophile. So this second product can be explained via the formation of this more stable carbocation. In other words, the reaction under option C is also possible, or the formation of all these products can be explained. So this reaction will take place. Okay, so the reactions under options A, B and C are all possible. We need to identify which reaction is not feasible or not possible. Look at the last reaction. First step, Cl. Now, chloride is not a very good leaving group. Iodide ion. It can act as a nucleophile and a base. It's a powerful nucleophile. If it is acting as a nucleophile, then you should get a substituted product. But look at the product written here. It's a product that has got a double bond. It is a product resulting from elimination. For elimination to happen, because the chloride ion is not a good leaving group, the base should be strong. But iodide ion is a weak base, and hence this reaction will not occur. Elimination will not occur, as a result of which option D is the correct answer. So I explained all these reactions in order for you to be more acquainted with the various shifts and shifts happening or resulting in the formation of more stable carbocations. It will help you to understand these concepts better. Okay, so D is the correct answer.